of this digitized data, and it collects information from several dozen to 100 institutions across the country, as well as around the world. Collectively, this website houses 6.4 million specimens. So, like I said, there's just a ton of data here, and it really hasn't been used to study things yet. So my project tried to use this data and see how useful this data is and what kinds of questions we can answer with that data. So something that could be used to answer, or this data could be used to answer questions is things like this. So mushrooms are becoming much more popular. They're trending right now. You might have seen them on your social media page. They've become like a wellness trend, as well as trend forecasters are noticing they're becoming like an aesthetic trend. So mushrooms are becoming popular, but also foraging as a whole is becoming popular. So here's an article from Scientific American in 2014, which is talking about this rise in foraging, in particular urban foraging too. And this has only grown since then, especially with the pandemic. People were kind of worried that grocery stores were running out of food, and they turned to foraging as an alternative option. And this trend isn't ubiquitous across the country, but looking here at the Google search trends, we can see that it's kind of focused in areas where mushrooms are very prevalent. So in the Northeast, Vermont and Maine, as well as in my study area, which is Washington and Oregon. So this increased interest in foraging and in mushrooms can lead to things like this. So this is, a huge harvest. People will go out into the woods and try to harvest as many of these mushrooms as they can. And maybe this is damaging to the population. There is some debate as to how damaging overharvesting is. But one thing that is for sure is that if there's more interest and more foragers going out, there's more people going off trail, more people potentially damaging native plant habitats or, certain protected species, as well as bringing pollution. So the first step into identifying that is knowing where these foragers are going. And then you can start to plan, like maybe we need different foraging laws, or maybe more trails should be built here to protect plant species. So my project took this herbarium data and tried to find where these popular areas were. And the species I chose for that is the Cantharellus formosus. This is also known as the Pacific golden chanterelle, and I chose this for several reasons. One, it's in a location with varied topography, which is pretty important when you're doing ecological niche modeling. You want to find somewhere that has a lot of different niches, a lot of different climates, different elevations, so that when you're doing the model, you can find areas that have certain niches, and it's not just ubiquitous across the study area. These next two things, number of records and cultural significance, kind of tie into each other. So the Pacific golden chanterelle is the state mushroom of Oregon. So it's very culturally significant, as well as it has a great economic significance. This mushroom hasn't been found, or people haven't found a way to commercially harvest this or commercially grow this. So the only way to get it is by foraging. And this cultural and economic significance kind of tie in and make it a very well-studied species and very well represented in herbarium records, as well as in the citizen science data. So this species is a good flagship for this methodology, because it has a lot of records and it meets these kind of criteria. So yeah, this was a good species, and here's what my project sought to do. Well, I wanted to use models, and I wanted to model specifically with this herbarium data. I also wanted to try and identify which model performed best, and I used a variety of them. So that was one question I wanted to ask. Using citizen science data was another big goal, and the idea behind including this was by having a second data set, I could get more statistically robust results. And the idea there is that if you have two data sets, they aren't correlated, And so your accuracy isn't being inflated by having correlations between your validation and your training data. And then finally, I want to correct for spatial bias with an effort variable. So these samples are just obtained randomly. They're downloaded from herbarium websites. There's no kind of methodology in the sampling. And as such, there could be some trends within that data. Maybe they're closer to herbariums. So I wanted to incorporate a way to control for that bias. Okay, so these are my goals. And let's see how I did that, how I went about doing that. So this is kind of a scary looking slide if you don't code, but this is my actual R code, and I did all my modeling in R. And so yeah, it's kind of just wanted to include that. So yeah, these were the models I tested, and kind of the important takeaway here is that the random forest and the maxent models, I couldn't incorporate that spatial bias, the mechanism to account for spatial bias. So going forward, just keep in mind that only the general linear model, as well as the artificial neural network, those were the two that I could account for spatial bias with. Now, some of you might be looking at me right now and thinking, what the heck is an ecological niche model? Well, let's just do a quick little rundown of the basic ideas behind it. So in this case, we have input points, and this example is a type of aquatic seaweed. So we have input points where we know that this species exists. Then we take environmental predictor variables, and these are things that we think influence the distribution of the species. So maybe salinity and nitrate concentration are very important to the species thriving in an area. So we take these layers and we are able to extract the data from those observation points. And from the data, from the predictor variables, this gets run through the models, and that's kind of what's going on with that cube thing. The models are looking at these and trying to see what is driving the distribution the most. And so once we have an idea of what's driving the distribution the most, we can make these suitability maps. But in my case, I wanted to insert a third aspect here, which was that spatial bias layer. So maybe in this example, the observation in Great Britain was underrepresented. We know that the species is there, but there weren't many observations taken there. So we could incorporate a spatial bias layer, which makes that one observation in Great Britain account more in the model. It has a higher weight. And so that's what I tried to do. And then finally, we're able to build these suitability maps, but we need a way to validate them to see how well they did overall. So these are the four pieces of information that I needed to start modeling. And I'm going to go through each one of these pretty briefly just to show you how I got them. So you already know the first one, the input points, and this is the herbarium observations over the study area of Washington and Oregon. I had 128 observations, which was kind of disappointing. When I originally downloaded the data set from the microportal, there was over 1,600 records. However, these are pretty old and they didn't have GPS tagging back then. So a lot of these had to get thrown out, and there were some duplicates. So while it is disappointing, I think it's kind of represents a snapshot of what this methodology looks like at the current moment. As more digitizing takes place and as more recent records get added to the herbariums, this should only improve further as more and more points are going to be able to be used, and this methodology will become more and more interesting. So yeah, this was my input points, and now I'm going to talk about the environmental variables. So on this slide, we can see that there's some big groupings here. I had things like precipitation, more physical measures of the environment as well, like soil and elevation. But the two big takeaways here are that the resolutions are different between these layers. And I settled on using a 250 meter resolution for all my layers going forward. And I felt this was a good middle ground to account for some kind of finer grain detail while also not making up too much data when downscaling the 800-meter rasters. The other thing to take away here is that this is 40 layers, and that's quite a lot. That's pretty unwieldy. I don't want to use these going forward through all my models, so I needed a way to get this down to a more manageable size. And I did that by what I'm kind of referring to as a pseudo bootstrapping technique, where I ran each of the models 10 times using a random split of 80% of the data. And doing this, I could get a relative estimate of how important each one of these predictor variables were not just on all the data, but on a random sample of the observation points. So it gives a more complete look at the study area as a whole. And doing that gave me these kinds of graphs here. And yeah, this is pretty overwhelming to look at. It's 40 layers times 4, so a lot's going on here. And let's make it a little more easier to follow. So what I was looking for in particular were what predictors performed well, like best overall consistently. So an example here is canopy cover, performed pretty well overall. And so going forward, this is definitely a predictor that I want to keep in my modeling. Another thing I wanted to look at is which ones aren't performing well overall. So an example of that would be these monthly average precipitation layers. They didn't perform very well, and I think the best one here is highlighted in red, that November in the random forest model. And you might think that's pretty high, why not include that in the model? Well, I wanted to keep the same layers between all 4 of them, and since these monthly average precipitations, they did okay in the random forest model, but they were almost negligible in the ANN and the GLM. So I decided to remove them. And so going forward, that would be 12 less. But we're still at 28, which is too much. So is there any way I can continue using this to refine it? And well, the answer is kind of no. You get things like this where should bio 12 be removed? It's kind of all over the place. So these middle of the road variables were more difficult to refine using this method. So I switched to a different process. Yeah, so here we see the bio 12 variable, and it's being compared to bio 18, and these layers look almost the same. And it makes sense that annual precipitation would correlate well with precipitation of warmest quarter. But if I were to include both of these in the model, there's a chance of reinforcing patterns that are just the result of random chance, that are the result of having the same data in 2 layers. So it's kind of increasing that trend increasing that based on randomness, not based off the actual habitat needs of the species. So it's good to get rid of one of these. And the method I used was by comparing all the remaining layers together against each other. And if they were more than 70% correlated to another layer, one of them would get taken out. So in this case, one of these, since they're more than 70% correlated, would get taken out. And doing that gave me these final 12 variables. And it just so happened to work out that there were 6 of the bioclimate variables, as well as 6 of the more physical measures of the environment. One of the big things here is that you see canopy cover stayed in, and that was one of those top performing predictors. And several of those did make it through this process, which was by design to keep those in place. So yeah, now I have these predictor variables, or these environmental predictor variables. I wanted to account for spatial bias. And so I created this cool looking map here. And this is what I called the effort variable. And so the effort variable was made by running a principal components analysis on 4 different layers. There was the distance to herbariums, distance to roads, road density, as well as terrain ruggedness. And the idea behind using this is that observations in lower effort areas are easier to come by, and so they shouldn't be as represented in the final model. And so that was the idea behind it. So in this case, observations in the white areas would be less represented, whereas observations in the more difficult to reach mountains, which might not have as many observations, but it's likely to be good habitat, should be more represented. So that was the idea behind that. And we can see here the herbarium points overlaid on top of the effort variable. So this was a good way, a good weighting scheme that I could use going forward. And then the final piece of information I needed was a way to assess the model quality. And I settled on using the citizen science data. And this was, again, designed to give more statistically robust results. So I used iNaturalist, and this is an app where users can go out into the woods or wherever and take pictures of species. These are then uploaded, and other users of the apps can vote on whether they think it is the correct species. And so the best observations get a higher grade, and I decided to take only the highest grade observations for this data set. So this is what that looked like. I had 259 points here across the study area. So now I had all those points that I had talked about in the brief overview of what the modeling looked like, and I could start on my actual modeling. So let's take a look at the results and see what I found. So this is what the output of the 4 models looked like. One thing to note here is that I used the TSS statistic, which is known as the true skill statistic, and the ETS statistic, which is the equitable threat score. I tended to focus more on the ETS score, since that has a way to account for the random chance that a model gets a prediction right, even though it wasn't necessarily the model's doing, it was just predicted there by chance. So that's what I used to compare between models. And it's pretty clear to see that the random forest model performed best overall. It's a little suspicious how well it performed. It's at 0.987, and the perfect score for it is a 1. So it's nearly perfect. And looking a bit closer at this, we can see that there might be a trend between those that didn't use the effort variable, which is those top 2, versus the ones that did use the effort variable. So going forward, just keep in mind that maybe not using the effort variable was leading to overfitting. First, though, I'm going to talk about what those importance values looked like. This is pretty similar to that big scary slide earlier with all the 40 importance values, but now it's just with the 12. So it's easy to see at the start that the Bio 4 performed really well, and this is temperature seasonality. And as a whole, it seems like this was the trend, that the bio variables performed much better than the more physical measures of the environment. This wasn't the case for the ANN though. That kind of was shifted. And this is maybe more what I was expecting to see at the start of the project, since traditional knowledge about foraging is you go to this slope or this aspect at this elevation, and then you start to find mushrooms. And to me, I think that I didn't see that trend as much. That's saying we're capturing more of a regional overview rather than getting those site-specific characteristics. So yeah, that was kind of interesting to see that the bio variables were more important. And then let's see what the effort variable, what effect the effort variable had. So this is 2 of the models, one with the effort variable and one without the effort variable. And it's pretty easy to see that the one without the effort variable overfit the study area much more. In particular, the Central Valley of Oregon, as well as around Puget Sound in Washington. These are more urban areas, much more farms, maybe suburban, less high quality habitat. And without the effort variable, that was being fitted. So the effort variable here seems to give us a much closer view to what reality would be. So that was kind of cool. And then seeing the ANN was much, it was basically that, but on steroids. So it was really good to see that the effort variable was performing as intended, and it was helping to get the final predictions to be more in line with reality. However, these differences visually are pretty big. But when looking at the statistics, there wasn't that much of a change. So here we see the ETS scores are almost similar. In fact, the one without the effort variable performed better. And same with the GLM, they're very similar. So one thing that could be going on here is that there's a difference in sensitivity versus specificity. And sensitivity is how well is the model at predicting true observation points, whereas specificity is how good is the model at avoiding areas that don't have observations. So with the effort variable, it wasn't as good at predicting observations, but it was much better at avoiding areas without observations. And the reverse is true for with the or without the effort variable. So that does indicate that there is overfitting going on here, even though the main statistic score isn't that different. Another thing that could be adding confusion was the decision to add 2 data sets. So here we see that the herbarium observations were much farther on average from roads, whereas the iNaturalist ones were much closer on average to roads. And the decision to use herbarium's observations as training, which were further away from roads to begin with, and then filter that through the effort variable, which is penalizing those lower distance to road observations, kind of maybe backfired by then testing the accuracy on these closer to roads observations, these lower effort ones. So that could have been creating some confusion in interpreting the results. So yeah, this is basically my main findings that I found. And let's do a quick wrap up looking at how well I performed with my project goals. So modeling with natural history data, that was my main goal. And I think this project does prove as a good proof of concept for this type of study. So I think like I was mentioning earlier, more points are needed. As more and more GPS tags points come in, this will become more interesting of a study. But right now, it was able to create models, and these models did line up pretty well with local knowledge of what the distribution should look like. The second goal I had was identifying which of the models perform best. And this was maybe left a little bit more difficult to interpret. So I think that confusion comes from having the effort variable placed on some, whereas some couldn't use the effort variable. So I think the best answer here is saying that the random forest model performed best. But there's the caveat that it might have been overfitting, and so it was the best without the effort variable, whereas with the effort variable, the artificial neural network performed best. Third, I have citizen science data. I wanted to include this, and originally this was included to get more statistically robust results, but it might have created some confusion because of the differences in their distance to roads, as well as then filtering it through the effort variable. So I think a future study might be able to improve or change my methodology by still including these citizen science data points, but by combining them and using some for the training data, and then maybe using a random split for the validation data. And then finally, I wanted to correct for spatial bias. And I think this was probably one of the more successful aspects of the study. It was pretty clear to see visually, at least, that using the effort variable helps align things much more with reality, much more with what we would expect. So yeah, the effort variable served to be a good indicator that this kind of methodology could be used with herbariums, and it is a good way to correct for biases within the unsystematic sampling. And yeah, these were my main goals. And so I think I achieved what I wanted to with this project. But thank you so much for listening, and please let me know if you have any questions.
All right, thank you, Zoe. If anyone wants to clap like for real, you can unmute yourself, or there are also the reactions in Zoom if you prefer that, or the chat, whatever you'd like. But we can open it up to questions now from anyone who has a question. I can't see anybody, so let me switch this to. So I'd say if anyone does have a question, just unmute yourself and ask, because we don't have that many people.
Just let me ask I suppose it's a general question, and I guess it's more specific. That was really interesting, Zoe. You in the abstract and elsewhere, then you talk about this BF model. You've got a skill score of 0.987.
Mhm.
Can you put that in some perspective? I mean, other researchers that have used that method to look at the distribution of perhaps other fungi, but more likely other plant species. What does that tell you when you get a score that's that close to perfect? And you touched on this in the presentation, but could you say a little bit more about that?
Yeah. Let's see, I'll go back to that slide and just kind of look at it. Yeah, so I think it indicates that there is like overfitting going on. And when you look at the random forest model here compared to the other ones, you can see that it covers a lot more of the study area. So it's getting a perfect score, I think, just because it's covering all of the possible areas that a point could be, and not necessarily because it's being as discerning with finding actual good areas, but it's just kind of saying everywhere is good. Whereas when you get into the other ones, there's more kind of a fine grain.
So therefore, when you use a model like that, maybe its practical significance is limited in a sense because you get such a great score. In the end, how predictive is it?
Right. Yeah. And I think that kind of there was that issue with interpreting my stats because it was too good. It was too good to be true, you know?
Right. Right. That's really interesting. Do you know what kind of scores others have there been studies using this method then to look at distribution of tree species, for example, or?
I think the rule of thumb is like over 0.7, over 0.75 is considered really good. Whereas like below 0.3 or 0.5 isn't very predictive. So yeah.
Any other questions?
I was going to ask this since nobody else is asking questions, and I'm hallucinating with my second dose of the Moderna vaccine. I guess I'll ask this in the general session. So, in your introduction, in the thesis, you talk about this work that actually goes back to the 1940s with looking at biogeography, looking at distribution of different species of fungi, and the fact that somebody identified that a particular fungus did seem to be endemic.
Mm-hmm.
And I wondered if you could try and put some of your results in that perspective of, how does this relate to that other work? So this issue in the biology of all microbes, that it's everything everywhere as long as the climatic conditions are supportive. But how maybe does your work fit within that framework?
Yeah, I think maybe this species is a good one for this kind of methodology because it had so many observations within the herbarium data set. But maybe it's limited in its application because it does seem to be fairly ubiquitous across the study area. So maybe this could be applied more so towards like rare species. I've seen some papers come out about like an endangered species in China where it was much more limited to a certain kind of environment, whereas this species seemed to be seem to exist more freely across the environment, I guess.
Right, right. Yeah. No, I think it's really cool the way this whole project began and using herbarium data. I think it's fascinating. Yeah.
Thank you.
Hey Zoe, I have a quick question.
Yeah.
You know, one of the things that was mentioned at the beginning was just sort of how the projects have all changed over the past year, just because of all the different circumstances. I was just wondering how yours changed and sort of how you adapted to still manage to get a really interesting project out of it.
Thank you. Yeah, I think my project was a little more resistant to the COVID pandemic than most, since I was data mining a lot of my stuff. Originally, there might have been like a trip out to the study area to talk to local foragers to see like kind of getting that local knowledge that way. It might not have been necessary, but it could have been an interesting thing to include. So that was kind of might have been in the cards, but ended up not being.
Cool, thanks.
Yeah.
I like that that was your question, Connor, who went to Hawaii in the middle of the pandemic. Oh my gosh. It's amazing you were able to do that.
Well, I mean, I was just really lucky. So I
Yeah.
mean, and my project would have been completely ruined.
Yeah.
So I was just wondering.
He was also really isolated, you know.
Yeah.
Yeah.
He wasn't in Waikiki. Any other questions? I'm looking to see if anyone's using the hand raising function or something, and I don't see anybody. Okay. So last call for questions from the audience. Oh, Nick's raising his hand again.
Well, just what's next for you, Zoe? So you've succeeded probably during,
Yeah.
depending on the vote in a few minutes, but during these pandemic circumstances, what's next for you? Professionally?
Yeah, I had originally been thinking about like a PhD program, but I think I've decided against that. So yeah, we'll see. I don't really know. I'm just trying to find a job now, and then maybe like a research position or something like cartography. I really like making maps, so something like that.
Yeah.
That was a good last question then. So if no one else has any questions, we'll just thank Zoe once again for an excellent presentation and beautiful slides as always.
Thank you for coming out. I really appreciate it.
You can unshare your screen now if you want to.
All right, yeah.
Okay, yeah, then we can see people better.
Yeah.
Thanks for coming, everyone.
Yeah.
And Lauren's defense is this afternoon at 1, right? You'll be fine.
Yeah.
You'll do great.
Yeah.
Thank you. Fingers crossed.
Yeah. Okay.
Thanks, everybody.